Hi, my name is Erick de Moura, founder and CEO at Cartesi. Cartesi is a project that started in early 2018 with the objective to make Dapps easier to build and much more powerful. We have been building a blockchain agnostic second layer infrastructure that allows the apps to move intensive computation over massive amounts of data off-chain while retaining decentralization and the same security guarantees of the underlying blockchain. Also, all the data involved can remain private among the interested parties in the application. Well, so far, there are quite a few projects that are also attaining these features in one way or another. But what really sets Cartesi apart is the fact that the app logic can actually be built using mainstream traditional software stacks on a real operating system. So actually, we provide a Linux runtime environment where the DApp logic can run. So you can use mainstream software stacks and also OS resources like the file system. That's quite unique, especially if you compare this to the very limited runtime environments and language, let's say, of Solidity, in which developers even struggle to convert numbers to string. Now, a few weeks ago, we released the alpha version of our first product, the Descartes SDK. The Descartes SDK is a product that provides superpowers to Ethereum, Dapps, and smart contracts. So smart contracts are able to specify a computation in the form of a full Linux OS and program that runs within it. And this computation will run by Descartes nodes that are run by the interested parties themselves. So actually, the DApp developer can choose a set of nodes that will run and verify computation off-chain. Typically, the nodes will be run either by the DApp user themselves or by people or organizations that they trust. The important thing about the way that these nodes achieve consensus off-chain is that as long as we have at least one honest node, the honest node is always able to ensure that the correct results of the computation is persisted on-chain. So we have a way now that's already available that smart contracts on Ethereum are able to specify these complex and intensive computations to run off-chain while retaining decentralization and the security guarantees of the main chain. So here's a graphical representation of what I just said. You have a DApp contract that's able to specify the computation, and the Descartes nodes that are involved run this computation off-chain. A claimer node presents the results to the blockchain, and the other validating nodes are able to verify the claim presented. And if one of the nodes see that the claim is false, that node is able to start a dispute and enforce that the correct result is persisted on-chain. So at the heart of the Cartesian node, we can find our VM, which is called the Cartesian Machine. The Cartesian Machine emulates a RISC-V ISA and is able to boot an entire Linux OS. It is deterministic, reproducible, and self-contained. These are fundamental properties to make sure that consensus is achieved. The other important feature is that the Cartesian Machine is transparent and it's able to produce a Merkle tree root hash of its entire states, and also Merkle proofs of parts of the states that show that the part of the state is consistent with the full state hash. It also is able to prove that the execution of one single microprocessor instruction advances the machine from one state to the next, and from one hash representing the states to the next state hash. This is very important because we also need a mirror implementation of the RISC-V ISA in order for the blockchain to verify the proof that one instruction actually takes the one state to the next state, which is fundamental for the dispute resolution protocol. Finally, when the developer is creating their DApp, they need to provide a Cartesian machine template. It's basically a template that receives a ROM specification, a RAM image that will contain typically the Linux kernel, a root file system flash drive, and a set of input flash drives and one output flash drive. So everything in the Cartesian machine is configurable. Actually, the app developer is able to choose the amount of RAM and number, position, and lengths of the drives over a 64-bit physical address space of the machine. Everything is configurable by the app developer according to the app needs. So for the Cartesian machine templates, of course, the input drives are empty at the beginning because these input drives are going to be replaced by drives that are going to be fulfilled with the actual information that is coming at runtime when the app is running. Here we have a sample of how we could instantiate a Cartesian machine using the command line interface. So you can easily see that through this command, one can pass a ROM image, a RAM image, specify the amount of RAM the root file system is giving through a flash drive. And when the machine boots, it just executes the sample command ls/bin, and then it halts. The Cartesian machine provides other ways for one to manipulate it from the outside. So we also have a Lua programming language interface, a C++ interface, and most importantly, a gRPC interface that's fundamental for the Cartesian machine to work inside the nodes and interacting with the blockchain. From the inside of the Cartesian machine, the program sees a full computer in a full Linux operating system. So it doesn't know that it is in an emulated environment at all. Let's give it a break for some time to talk about some cool application that we delivered at the beginning of this year. Crypts is a tower defense game in which the players compete against each other for the highest score. It's fully decentralized. It runs on Ethereum thanks to Cartesi. What's cool about Crypts is that it involves heavy processing. You have billions or even trillions of microprocessor instruction steps that are required to run in order to verify a gameplay. And of course, doing that on-chain would be impossible due to the computational limits of the blockchain. The second important thing is that Crypts was implemented using TypeScript, and it does, among other things, compression and decompression of files, which of course would also be impossible to do on Ethereum because the concept of files is not there. So here we have a fully decentralized tower defense game involving heavy computation and mainstream software stacks and OS resources, totally working on Ethereum thanks to Cartesi. So if you want to try, you can just download, it's open source. You can even use it as a template to build your own game. Let's go back to how Cartesi works. So we spent some time talking about the RISC-V VM architecture, which is one of the pillars of the technology. And the other pillar is the local consensus protocol. I'd like to spend some more time talking about the local consensus protocol. It's a very important aspect of the system. If you were to develop a game on Ethereum or any blockchain supporting smart contracts, and let's say Alice and Bob would challenge each other on this game, then for every single game move that Alice or Bob do, it becomes a transaction in the Ethereum blockchain, and that transaction with entailed computation needs to be emulated by around 12,000 full nodes in the network. And of course, the 12,000 nodes are not interested at all in the results of the match between Alice and Bob. That doesn't concern them. So it's really a waste to involve so many people doing this computation for the two players that are competing in the game. So the smart approach here is to instead let Alice and Bob play the game totally off-chain, and at the end of the game, when, let's say, Alice wins the game, she just goes to the blockchain, and a single transaction is needed only to settle the resolution of the game and perhaps give Alice her token reward or something like this. Of course, it only works if it prevents any kind of cheating that could happen from Bob. So if Bob is honest and he recognizes that Alice won the game, then everything runs smoothly. Alice just presents the blockchain that she was the winner. Now, of course, Bob can go evil and he can pretend to be the winner of the game. And then we need to have some mechanism so that Alice can infallibly prove to the blockchain that she actually won the game. And that's the mechanism that's behind Cartesi. So for this to work well, we also need an incentive structure, because we don't want these things to happen, right? We don't want Bob to go evil and try to cheat. That should be the exception. So what happens if Bob tries to cheat is that Alice can go to the blockchain and start a dispute resolution protocol. For that, she places a collateral deposits on a smart contract, and she's not worried because she knows that she can prove to the blockchain she won the game, and she's going to recover later her collateral back. Now, two things can happen. First, the challenging period just expires and Alice wins by timeout because Bob didn't show up, and the blockchain assumes that Alice won the game and returns to her the collateral. The other possibility is that Bob goes crazy and really tries to fight back against Alice. Of course, he's going to lose because he cannot prove to the blockchain, whereas Alice is able to prove that she is a rightful winner. And in that case, Alice is twice as happy because she not only recovers her collateral, proves she won the game, but she also gets the collateral that has been slashed from Bob. So how it all works together. Cartesi is a blockchain agnostic second layer infrastructure that allows the apps to move intensive computation over massive amounts of data off-chain while retaining decentralization and the same security guarantees of the underlying blockchain. In the rare cases of disputes, the blockchain is used as a supreme court, and only a negligible amount of the original computation needs to be run on-chain. We also saw that the Cartesian machine employs Merkleized representations of its internal states, and that's fundamental for the system to achieve consensus. We also saw that we have an off-chain and an on-chain implementation of the RISC-V ISA. The on-chain implementation is necessary to make sure that in case disputes happen, the blockchain can verify one microprocessor in step instruction so that the honest claimer can make sure his claim succeeds on the blockchain. The algorithm that we use for dispute resolution is an interactive dispute resolution protocol called the verification game. It's a protocol that's used by other projects like TrueBit. If you want to know more about this protocol, we have extensive documentation explaining this on our website, on our tech paper. and you can just go to cartesi.io. From there, you're able to find all the documentation you need to understand Cartesi in depth. You can also find our contacts from there, and it will be a pleasure to talk more to you. Thank you.